The earlier history of conic sections among the Greeks, Chapter 1. The discovery of conic sections, Menaechmus. There is perhaps no question that occupies comparatively a larger space in the history of Greek geometry than the problem of the doubling of the cube. The tradition concerning its origin is given in a letter from Eratosthenes of Cyrene to King Ptolemy Euergetes, quoted by Eutychius in his commentary on the second book of Archimedes' treatise on the sphere and cylinder. And the following is a translation of the letter as far as the point where we find mention of Menaechmus, with whom the present subject begins. Eratosthenes to King Ptolemy, greeting. There is a story that one of the old tragedians represented Minos as wishing to erect a tomb for Glaucus, and as saying, when he heard that it was 100 feet every way, too small thy plan to bound a royal tomb. Let it be double, yet of its fair form fail not, but haste to double every side. But he was clearly in error, for when the sides are doubled, the area becomes 4 times as great, and the solid content 8 times as great. Geometers also continued to investigate the question in what manner one might double a given solid while it remained in the same form. And a problem of this kind was called the doubling of the cube, for they started from a cube and sought to double it. While then for a long time everyone was at a loss, Hippocrates of Chios was the first to observe that if between 2 straight lines of which the greater is double of the less, it were discovered how to find 2 mean proportionals in continued proportion, the cube would be doubled, and thus he turned the difficulty in the original problem into another difficulty no less than the former. Afterwards, they say, some Delianas attempting, in accordance with an oracle, to double one of the altars fell into the same difficulty. And they sent and begged the geometers who were with Plato in the academy to find for them the required solution. And while they set themselves energetically to work and sought to find 2 means between 2 given straight lines, Archytas of Tarentum is said to have discovered them by means of half cylinders, and Eudoxus by means of the so-called curved lines. It is, however, characteristic of them all that they indeed gave demonstrations, but were unable to make the actual construction or to reach the point of practical application, except to a small extent Menaechmus, and that with difficulty. Some verses at the end of the letter, in commending Eratosthenes' own solution, suggest that there need be no resort to Archytas' unwieldy contrivances of cylinders, or to cutting the cone in the triads of Menaechmus. Thus, the evidence so far shows, first, that Menaechmus, a pupil of Eudoxus and a contemporary of Plato, was the discoverer of the conic sections, and second, that he used them as a means of solving the problem of the doubling of the cube. We learn further from Eutychius that Menaechmus gave 2 solutions of the problem of the 2 mean proportionals, to which Hippocrates had reduced the original problem, obtaining the 2 means first by the intersection of a certain parabola and a certain rectangular hyperbola, and secondly by the intersection of 2 parabolas. Assuming that A and B are the 2 given unequal straight lines and xy the 2 required mean proportionals, the discovery of Hippocrates amounted to the discovery of the fact that from the relation A over x equals x over y equals y over b, it follows that x cubed equals a squared b, and if a equals 2b, a cubed equals 2x cubed. The equations are equivalent to the 3 equations, x squared equals ay, y squared equals bx, and xy equals ab. And the solutions of Menaechmus described by Eutychius amount to the determination of a point as the intersection of the curves represented in a rectangular system of Cartesian coordinates by any 2 of those equations. The first solution now consists in drawing a parabola with vertex O and axis OX such that its parameter is equal to BO or B, and a hyperbola with OX and OY as asymptotes such that the rectangle under the distances of any point on the curve from OX, OY respectively is equal to the rectangle under AO, BO, that is to say, to a B. If P be the point of intersection of the parabola and hyperbola, and PN, PM be drawn perpendicular to OX, OY, that is, if PN, PM be denoted by YX, the coordinates of the point P, we shall have Y squared equals BX and XY equals AB, whence A over X equals X over Y equals Y over B. In the second solution of Menaechmus, we are to draw the parabola described in the first solution, and also the parabola whose vertex is O, axis OY, and parameter equal to A. The point P where the 2 parabolas intersect is given by y squared equals bx, x squared equals ay. whence, as before, a over x over y equals y over b. We have therefore in these two solutions the parabola and the rectangular hyperbola in the aspect of loci, any points of which respectively fulfill the conditions expressed by the equations. And it is more than probable that the discovery of Menaechmus was due to efforts to determine loci possessing these characteristic properties, rather than to any idea of a systematic investigation of the sections of a cone as such. This supposition is confirmed by the very special way in which, as will be seen presently, the conic sections were originally produced from the right circular cone. Indeed, the special method is difficult to explain on any other assumption. It is moreover natural to suppose that after the discovery of the convertibility of the cube problem into that of finding two mean proportionals, the two forms of the resulting equations would be made the subject of the most minute and searching investigation. The first form, expressing the equality of three ratios, led naturally to the solution attributed to Plato, in which the four lines representing the successive terms of the continued proportion are placed mutually at right angles and in cycle order round a fixed point, and the extremities of the lines are found by means of a rectangular frame, three sides of which are fixed, while the fourth side can move freely parallel to itself. The investigation of the second of the equations led to the attempt of Menaechmus to determine the loci corresponding thereto. It was known that the locus represented by y squared equals x times x2, where y is the perpendicular from points on a fixed straight line of given length, and x1, x2 are the distances into which the line is divided by the perpendicular, was a circle. And it would be natural to assume that the equation y squared equals ax, differing from the other only in the fact that a constant a is substituted for one of the variable magnitudes, would be capable of representation as a locus or a continuous curve. The only difficulty would be to discover its form, and it was here that the cone was introduced. If an explanation is needed of the circumstance that Menaechmus should have had recourse to any solid figure, and to a cone in particular, for the purpose of producing a plane locus, we find it in the fact that solid geometry had already reached a high state of development, as is shown by the solution of the problem of the two mean proportionals by Archytas of Tarentum, born about 430 BC. This solution in itself, perhaps more remarkable than any other, determines a certain point as the intersection of three surfaces of revolution. First, a right cone, second, a right cylinder whose base is a circle on the axis of the cone as diameter and passing through the apex of the cone. Third, the surface formed by causing a semicircle whose diameter is the same as that of the circular base of the cylinder and whose plane is perpendicular to that of the circle, to revolve about the apex of the cone as a fixed point so that the diameter of the semicircle moves always in the plane of the circle. In other words, the surface consisting of half a split ring whose center is the apex of the cone and whose inner diameter is indefinitely small. We find that in the course of the solution, the intersection of the surfaces 2 and 3 is said to be a certain curve, being in fact a curve of double curvature, that is, a circular section of the right cone is used in the proof, and as the penultimate step, two mean proportionals are found in one and the same plane triangular section of the cone. The solution of Archytas is, like the others, given by Eutocius and is so instructive that I cannot forbear to quote it. Suppose that AC, AB are the straight lines between which two mean proportionals are to be found. AC is then made the diameter of a circle, and AB is placed as a chord in the circle. A semicircle is drawn with diameter AC, but in a plane perpendicular to that of ABC, and revolves about an axis through A perpendicular to the plane of ABC. A half cylinder, right, is now erected with ABC as base. This will cut the surface described by the moving semicircle APC in a certain curve. Lastly, let CD, the tangent of the circle ABC at the point C, meet AB produced in D. And suppose the triangle ACD to revolve about AC as axis. This will generate the surface of a right circular cone, and the point P will describe a semicircle BQE perpendicular to the plane of ABC, and having its diameter BE at right angles to AC. The surface of the cone will meet in some point P the curve described on the cylinder. Let APC prime be the corresponding position of the revolving semicircle, and let AC prime meet the circle ABC in M. Drawing PM perpendicular to the plane of ABC, we see that it must meet the circumference of the circle ABC because P is on the cylinder which stands on ABC as base. Let AP meet the circumference of the semicircle BQE in Q, and let AC prime meet its diameter BE in N. Join PC prime QM QN. Then, since both semicircles are perpendicular to the plane ABC, so is their line of intersection QN. Therefore, QN is perpendicular to BE. Hence, QN squared equals BN multiplied by NE equals AN multiplied by NM. Therefore, the angle AQM is a right angle. But the angle C prime PA is also right. Therefore, MQ is parallel to C prime P. It follows by similar triangles that C prime A divided by AP equals AP divided by AM equals AM divided by AQ. That is, AC divided by AP equals AP divided by AM equals AM divided by AB, and AB, AM, AP, AC are in continued proportion. In the language of analytical geometry, if AC is the axis of X, a line through A perpendicular to AC in the plane of ABC, the axis of Y, and a line through A parallel to PM, the axis of Z, then P is determined as the intersection of the surfaces. X squared plus Y squared plus Z squared equals A squared, that is equation 1. XY plus Y squared equals AZ, that's equation 2. X squared plus Y squared plus ZA equals square root of X squared plus Y squared, that's equation 3. Where AC equals A, AB equals B. From the first two equations, X squared plus Y squared plus Z squared equals the fraction A squared times X squared plus Y squared over Y squared. And from this equation and equation 3, we have A over square root of X square root of X squared plus Y squared equals square root of X squared plus Y squared over Z squared equals Z over square root of X squared plus Y squared. Therefore, AC divided by AP equals AP divided by AM equals AM divided by AB.